whereby certain materials are attracted by an externally applied magnetic field. It possesses a permanent dipole moment. Here you can see in the diagram, the first one, before applying the magnetic field, the magnetic dipole moments are aligned in a different manner and they are totally randomly aligned, where H is equal to 0 and M is also equal to 0. But when you apply the field, they try to move and they try to be aligned in a particular direction, which is the direction of the external magnetic field, and where H is equal to H0 and M is equal to positive M0. That means this type of materials are magnetized, right? So in paramagnetic material, okay, again we are moving ahead. If we remove the external magnetic field, they will align themselves again in their original position, or say they will be again randomly aligned. So they are magnetized, but they do not sustain magnetization. So in the absence of external magnetic field, the dipoles are randomly oriented due to the thermal motion, but then and the net dipole moment is 0. But if external magnetic field is applied, the magnetic moments of individual atoms align themselves in the direction of the field, and so the net dipole moment will be non-zero and it will give the non-zero magnetization. What are the properties? Paramagnetic materials possess a permanent dipole moment. Magnetic dipole moments are aligned randomly, as I told you. They attract magnetic lines of force, that means external magnetic lines of force. The susceptibility is positive and it depends on the temperature. The temperature is defined by Curie law. It is called the Curie law of paramagnetism, where C is the Curie constant and T is the temperature. You can see the equation chi is equal to C divided by T. Paramagnetic susceptibility is inversely proportional to the temperature. What are the, as you can see from this equation, it is well proven. What are the examples? Aluminium, chromium, sodium, titanium, zirconium, etc. Now we are going to move to the next type of magnetic material, that is ferromagnetic material. Ferromagnetism is the basic mechanism by which certain materials such as iron from permanent magnets form a permanent magnet or attracted to the magnet. Here is a material which is very important, ferromagnetic materials. When you remove external magnetic field, even if they possess the permanent dipole moments, and what happens? They actually possess the permanent dipole moment. So you can see here that they are attracted by a magnet, and in the lowermost diagram you can see their dipole moments are randomly aligned, where weak interaction is there, and under the strong interaction with the magnetic field they are moving in a particular direction. You can say that it possesses permanent magnetic moment, which is mainly due to the spin magnetic moment, that is the electrons are moving with a particular spin and due to them they possess a permanent magnetic moment. They are aligned parallel to the external field, but before you apply the external field they are already aligned in a particular direction. So in this type of magnetic material there are areas, or say domains, they are actually in which all the magnetic dipoles are aligned in a particular direction, and this domain's resultant magnetic field, dipole moment, they are giving a non-zero value to the particular domain. So due to this interaction they are aligned parallel to each other. The ferromagnetic materials exhibit spontaneous magnetization even in the absence of the external magnetic field. Due to the strong internal field which exists already in the material, the alignment of the magnetic dipole moment results, and in this domain all the domains, the wall between two domains, they are known as domain walls, and when a small magnetic field is applied it produces a large value of magnetization due to the parallel alignment dipoles. And in a ferromagnetic material, the influences of internal and external fields make them different from other magnetic fields. The molecular field theory, or say wave theory, is used to explain the ferromagnetic properties of the materials. Here you can see, as I told you, there are domains shown. You can see the different directions of the resultant dipole moments of the domains. You can see in the presence of magnetic field, they are aligned in a particular direction, but in the absence of actually in the presence of magnetic field, they are aligned in a particular direction. If I remove the magnetic field, even then they do not exhibit that they will align in random direction. They will be there in aligned in a particular direction of the external magnetic field. What are the properties? They possess permanent dipole moments, they attract the magnetic field line of force, they have characteristics temperature, ferromagnetic Curie temperature. In the absence of a magnetic field, it exhibits magnetization, which is due to the property of spontaneous magnetization. The susceptibility of the ferromagnetic material is chi C divided by T minus theta, where C is the Curie constant and Q is the paramagnetic Curie temperature. Examples: iron, cobalt, nickel. Antiferromagnetic materials. In ferromagnetic materials, magnetic dipoles are parallel to each other, as we say, and in antiferromagnetic material, the magnetic dipole moments, they are anti-parallel to each other. The exchange interaction leads to anti-parallel alignment of dipoles. Mind well, their magnitudes are same, and hence the resultant magnetic moment is again 0. So magnetization is also 0. The anti-parallel alignment exists in the material below a critical temperature known as Néel temperature. You can see here in the diagram, their magnitude is same, but they are aligning opposite to each other. So when this temperature increases, the susceptibility increases and reaches to a maximum at a temperature known as I told you, Néel temperature Tn, beyond which it decreases. The value of the susceptibility is positive here. And what are the examples? Ferrous oxide, manganese oxide, manganese sulfide, and chromium oxide. Ferrimagnetism, it is the fifth type of magnetic material. If a special case of antiferromagnetic materials, you can see here, magnetic materials, all the four magnetic materials, say the antiferromagnetism, they have the dipole moments align opposite to each other, and here you can see that these dipole moments, they are aligned opposite to each other, as well as their magnitude is not similar. You can say that the magnetic dipoles are antiparallel, similar to an antiferromagnetic material. Their magnitudes are not equal. This is due to the magnetic interactions existing between dipoles. Ferrimagnetic materials possess net magnetic moments due to the antiparallel dipoles with different magnitudes. They produce large magnetization even for a small applied external field. You can see here again that the picture is the picture shows that the magnetic dipole moments of a particular material, here is a ferrimagnetic material, they are aligned opposite to each other, but they are not equal in magnitude, right? So that is due to the interaction amongst the dipole moments, and then net dipole moment is not 0. Then how will it behave under the external magnetic field? That will be depicted by the properties. The dipoles are antiparallel, however the dipoles are not equal in the magnitude. So net magnetization is larger even for a small external field. For paramagnetic materials, when you apply an external magnetic field, you require a sufficient amount of external magnetic field to magnetize the material. Why? Because the dipoles are randomly oriented. But for all another three, ferromagnetic, antiferromagnetic, ferrimagnetic materials, you require a very small amount of magnetic field just to make the dipoles change their direction. Why? Because they possess permanent dipole moment, and they are ready to move into the external magnetic field. So they are very positive in the response to the external magnetic field. Coming back to the ferrimagnetism, here net magnetization is larger. The susceptibility is positive and very large when the temperature is higher than which temperature? The Néel temperature. They behave as paramagnetic and ferromagnetic materials respectively above and below Curie temperature. So below Curie temperature they behave as paramagnetic material, and above Curie temperature they behave as ferromagnetic material. The same way for ferromagnetic material, up to a certain extent it will show a very strong magnetization because their dipoles are aligned in a particular way, but after a certain temperature sorry, they behave as paramagnetic material. Ferrimagnetic domains are used as the magnetic bubbles in memory elements. You can see here the graph of flux density versus mu 0 h. In the fourth quadrant, we will start with diamagnetic material where mu is less than mu 0. That means the absolute permeability is less than the permeability of the space. You can see the dipole moments are aligned in a different way. There is a particular line for the external magnetic field, and you can see here. Thereafter there is vacuum. Then paramagnetic material is mu greater than mu 0. Again you can say the dipole moments are aligned in random way in the presence of external magnetic field. The ferrimagnetic material there comes where mu is very greater than mu 0, and you can see their dipole moments are aligned in such a way that they are opposing each other in the presence of external magnetic field, but their magnitude is not equal. And ferromagnetic material, there again mu is very greater than mu 0, and that means all the magnetic dipole moments, they are aligned parallel to each other in the presence of external magnetic field, and they are ready to be magnetized. That means on the hysteresis loop, what type of hysteresis curve will you get for ferromagnetic materials? Yes, you are right. The magnetization is very high in the presence of very less magnetic field, right? Now what is hysteresis loop? Hysteresis is a curve which shows the effect of the external magnetic field. That means it is BH curve, B versus H curve, right? So the value of the BH curve, or say the value of the magnetization, that will be calculated through the hysteresis curve. First thing. Second thing, the value required to magnetize a material, value of the magnetic field required to magnetize a material, that can be found from the hysteresis curve, as well as the value of the magnetization at which the magnetization is maximum, that can be also found from the hysteresis curve. And also with the area under the curve, or say area enclosed by the hysteresis loop, that with that you can find out the energy loss inside the material in order to magnetize the material, that can be also found from the hysteresis curve. Okay, this is the end of the first part of the magnetic material. Another part of the magnetic material chapter, that we can see in the next lecture. Thank you.